Hello?
Okay.
It works. Oh, great. Thanks.
All right, brilliant. And the second talk in this session is by Weixi, who will tell us about the type system for feature engineering.
Yeah, thank you. If I can find my mouse. Where's my mouse?
The other screen, possibly?
It doesn't move to the other side. Oh, okay. So that's the left one. Great. All right. My name is Weixi. It's great to be here. So I'm gonna present a work that we have built at Meta. So basically, we built a small compiler for kind of a SQL-ish DSL, and so for feature engineering. So basically, what we have built is rather straightforward. But what's interesting is the context, like how do we use the tricks from building type theory for feature engineering. So let's start from there. So I guess for everyone in this room, when you see this title, the response will be, what on earth is feature engineering? So let's start with that. And for the people who actually work on feature engineering, their response will be totally different. Well, what on earth is a type system? Well, what it does? So we will go in, maybe we'll spend 1 minute on that since everyone knows what's it. So let's say I'm going to teach Agda to some undergrad students, right? So maybe I want to write a machine learning model to predict how well received my class will be. So basically what this model is, if this person may like Agda. So this is a model and you need the inputs for the models, right? So you're going to come up with some data, like how about maybe the line of Haskell programs this person has written, or the number of induction proofs, or maybe if this person fancy Unicode because it doesn't exist in Haskell. And so anyways, so these are kind of the inputs to this model, and we call them features. So that's a fancy way of saying models, inputs to models. And so what is feature engineering? So maybe if I'm a domain expert of, say, teaching dependent types, I may realize, probably, the number of Haskell programs written and the number of induction proofs written are kind of the similar thing. So maybe before I feed them into the model, I may want to add them together, use as a one number, so that, my model may perform, more efficiently or more accurately. I don't know, but that's the idea, right? So that's feature engineering. And so basically, it's just transforming data. And so it's a SQL-ish language. And so in this talk, I'm going to cover just a very handful, like 3 operators, but it's going to give a meaningful example of what we are doing here. So the first is, so we have a table, right? 3-person, X has written 100 lines of Haskell, Y 42, Z is -10. So yeah, how can it be negative? Maybe they wrote too much Python or C++ and whatever. Yeah. So the first operator is very straightforward. It's just adding a new column. Column called this number is divided by Haskell by 2. So we are adding a new row here, a column here, and so that's add. So see, basically the entire DSL is like this. You have operators, and this operator you can just embed some, let's just say, ordinary lambda expressions here. So it's the operators that are interesting. And the second operator is filter. What it does is to manipulate with the row numbers. So if I just want to ignore everyone who has negative number of Haskell written, I just filter Haskell larger than 0, and this unlucky person is gone. And right. So, and what's the most interesting one? This is covered in the talk in the early morning one. It's called left join. So what it does is it takes 2 tables. So they may have something in overlap. So maybe the names XYZ and these names. So they may not be completely overlap. Like you have X in the first table, but not in the second table, right? So when you do this left join, there's some magical semantics happening. That is, every row from the left parent will be preserved. So you see X, Y, Z are all here. And from the right parent, only the rows that match the condition will be preserved. So because we are checking the equivalence of names, so you see W does not exist in the first table, so it's gone. And and on the other hand, this Z here, it doesn't have a correspondence in the second table, so it has a none. So basically everything is a kind of a maybe type. So that's the three operators, and that's good enough to show what feature engineering does. And okay. And now, so just like ordinary programs, there are many different ways to write the same feature. So if you think about semantics, what left join does is to preserve everything from the left parent. So if you have a filter on the left parent, then it's perfectly safe to move it below the join operator, and it's the same program. You compute to the same table. So that's kind of the equivalence, and it's kind of the crux of the matter. And okay, now what is the problem? So we have looked at this kind of the smaller picture of feature engineering. That is how one person, say one engineer, may write a piece of program. And what about everyone in the company? So there are a lot of problems. So our work started by the third author asking me this question. Hey, Weixi, can you use your type system to do semantic validation? Back then, I didn't know what on earth is semantic validation, and I said yes. So because I have faith in our type system. So turns out to be, here's the more elaborated description. That is, so we have a compiler, right? And you see we can move this filter around, right? And so one particular thing about this compiler is we are compiling to different backends. So maybe one function runs more efficiently in one backend, but not the other. So we need to change the shape of the graph. And we need to validate if the transformations we are doing is correct. We're not like accidentally dropping rows. So that's the first challenge we were facing. And the second thing is preventing duplications. So something very particular about our compiler is we do not compile only one program. We compile like 100,000 programs simultaneously, kind of global. So one interesting thing is how do we find duplications? Because do you really have 100,000 different ways to compute different features? Probably no. And so if we can cut down the duplications and probably merge the same nodes in the graph, we can save a lot of power. So that's a second problem. And the third kind of problem is we want to build a queryable kind of data. That is, if we have that many features and we need to check, say, privacy policies or some regulations, or maybe you just know if a feature contributes to the revenue of the company very much. So we need to query those features over and over. And it's just impractical to just run that 100,000 features every single time because every may have like hundreds of nodes. So that's difficult to do. So those are kind of the problems we are facing. And so far we have used this type system to solve the first problem. We are working on the rest too. So let's look at how do we do that. And so that's kind of the background for feature engineering. And for people who don't know type system, and so if maybe not in this room, maybe someone's listening on YouTube, maybe my colleagues. Anyways, so basically type inference is you have a program like 42 and you generate a number like int. So that's kind of the simple type. And if you have dependent type, things becomes a little bit more interesting. Say if I'm appending two lists, the first list is empty, the second one is just 1, 2, 3. And so of course my type system gonna tell me, well, it's a list containing ints, there are 3 elements. But if you have built a, say, dependent type language, then a trick that you often use is you're gonna store the normal forms or kind of the intermediate states of your program, because like this 1, 2, 3 is the normal form of empty list appending to 1, 2, 3, because you're gonna use it over and over. And so the trick is in our type system as well, types are actually data types plus the normal forms. And so let's talk about the normal forms. And so normalization by evaluation, that's the core of our little type system. So the idea of normalization by evaluation, I'll go over it very quickly because probably everyone knows it. If you have different ways of writing expressions, like double applying on 21 and any other way, and they will be reduced to another domain, maybe a value called 42. And then you read this 42 back, so you now map many different expressions to one unique expression. And things can get a little more interesting when you have variables and binders. So maybe you're gonna do some variable elimination or called alpha equivalence using the Brown numbers or one way or another, and maybe you can do some swapping of the order. So that's the general idea. And now let's go back to this feature engineering problem. So we have this very simple grammar. We have, let's say, 3 or 4 operators, and we have some expressions. So here's what we did. So basically, let's say we have a table. We have 2 tables. The first table has names and the number of Haskell programs written. The second table is names and the number of induction proofs written. Right. So I'm say filtering out the first table on people who has positive number of Haskell programs doing a left join, and I'm adding the number of Haskell and the number of induction. So as we just went over before, there are 2 ways or many different ways to write the same program, because you can move this filter node around. So and now the problem is very straightforward. So we have 2 different graphs that may be seemingly different, but they can be type checked or type inferred to the same type. So here is the type. It consists of 3 parts. One is kind of more conventional, ordinary data types, 3 fields, string, integer, and integer. I mean 4 fields. And the second is about the conditions. Because in the SQL language, what we are doing here is, we manipulate the row numbers. And so basically what we had done is to design kind of a value form for the SQL expressions. And so when you have a filter, you are reducing row numbers. And maybe when you're doing a join, you have some condition here. You are doing some kind of another conditions. So we are doing a normalization on each expression of this filter and put them in this K or kappa for conditions. And the third one is row. I choose this letter row because it's like when you're writing an interpreter, row is an environment. It captures the computation of every variable in your visible scope, right? So, and this environment here, it will kind of normalize every added variable like x here, all the way to all the functions it has went through, all the what's that? Operators it has went through, and all the way to the table. Like here, let's say that look at this induction here. That's an interesting point. So here, because it's from the right parent of a left join, so some rows in this induction will be lost. And so what we're doing is just simply adding a tag, saying, there's a join. So now we know this join on induction is different from induction itself. So that's kind of the result. And let's say if we have another join, maybe a right join, which is different from the left join, because in a right join, you're going to preserve everything from the right parent, but you're going to lose something from the left parent. Now, these 2 programs are going to compute to 2 different types, because if you normalize the filter node, the first one, you have the row loss after the lineage, after the filter. So if you look at the lineage of induction, it's just from the original table. It's saying nothing happened to the original table. But if the filter node happens after the right join, and then you can see this tag here, so they will be different. And so, okay, so yeah, that's the idea. I guess so. Before most work on type system is designed for humans, like how do you catch more bugs. So maybe another perspective is maybe you can use it to for the machines to detect more things. Okay. So to quickly sum up, we designed a kind of a type for the tables in a SQL language, particularly for feature engineering. Consists of 3 parts: the data types, the conditions, and the environment or the computations. And so here's a example of the inference rule of this filter. If I'm filtering this table T0 on some condition K, So first off, this table itself has a type, a triple, types, conditions, and environment. And then this k got to be a bool. So as a result, we are kind of evaluating or normalizing this new condition here, adding it to the original conditions. So that's filter. And for live drawing, it's kind of similar. And we have many operators, like 20 of them. So if an operator somehow impacts the row numbers, we're gonna just add a tag to all the computations that it involves, so that we know, well, this one is changed. Right. So I guess that's it. Thank you.
Thank you very much, Weixi, and we have plenty of time for questions. So.
So first a remark. You said, what if we were using types for machines? Actually, historically, I mean, Fortran was designed with types so that the compiler could produce faster code. So I mean, it's not crazy. Now for the join attack, so I see what you're doing. In a sense, if I were doing this in independent types, and it's actually a traditional issue, right? If you have a filter function over vectors, so vectors list index by the length, you apply a Boolean predicate over the elements in the list, then what's the type of a resulting vector? We don't know. So we put an existential, or we do. So join here seems to be playing the role of an existential. There exists some size of table, but then it doesn't name. So are you using it for something in particular, or are you hoping that when you see this join tag in your types, you can do something clever?
So for now, it's only to differentiate a column that being joined, being impacted by join, or not being impacted by join.
All right.
Yeah.
Okay.
But yeah, that's an interesting point.
Okay, thanks.
Yeah. Okay.
Any other questions?
So you mentioned at the start that you said you had 600,000 programs or something that you were trying to compile down.
More than 100,000.
More than 100,000. Sorry, the number anything more than 10 is pretty large. Why do you end up with such a large number of programs?
I don't know if I.
Oh, you're maybe not allowed to say.
Yeah.
That. Sorry. Okay.
I guess when I joined, there are already that many joined the company. It's, I guess in real engineering, it's very difficult to control everything, and so.
Okay, so it's some sort of optimization process over the top that is generating these different candidate programs or something like that.
Yeah.
Okay. Okay. Cool. Thanks.
So I guess I'm just wondering. So since we're sort of doing like a feature engineering here, I'm wondering like where in the process of engineering would you like want to use this sort of program for doing these kind of things, I guess.
Oh yeah. So it's kind of okay. So about feature engineering, it's like this. There are some we call ranking engineers who write SQLs and throw them into machine learning models, and they invoke the compiler. So during the compilation, we're gonna capture, we say, the semantics or this triple of that feature, or some important nodes of that feature. We're gonna store it physically somewhere. And and then if someone else writes another feature, we're gonna kind of run a query to detect whether this feature already exists. If this triple is already there, so that's basically what we are doing, and that's about authoring features. And there are some other mechanical processes, like we want to query, say the value of each feature, and that's also. That's an external process.
I see. I'm wondering if so you have like sort of like a database of like features, I guess you would say.
Yeah.
And so I guess there's like some data describing like
Exactly.
where it came from, right?
That's a really good point. So actually, one thing we are building right now is kind of trying to build a relational programming language, I don't know, or similar. So like you can query it like in Facebook, there's a open source library called GraphQL. It's a kind of relational programming language. So what it does is maybe I have a feature name and I want to query what are the fields, what are the table fields it's using, right? So that's some relation, and other kind of relation is something like that.
Yeah, it sort of reminded me of like when your first example where you had like the sort of the symmetry like thing, kind of reminded me those programs back when they would just like you would like run this sort of like I guess like entropy program, and it would like find like the
Right.
symmetry that best sort of matched based on
Yeah, exactly.
some sort of principle, right? And so that's what it sort of reminded me of, and I guess it leads into the question of like a lot of these like programs, it's sort of hard to I guess decide how it's equal. Like say like you're using like some machine learning algorithm, right?
Mm-hmm.
How can you know if they're sort of equal? I guess is what I'm trying to I guess understand. Like I'm not really sure if it's relevant, but I guess I'm just sort of wondering how you would put like a sort of program like like a neural network, for example, where it's kind of hard to compare and stuff like that. Like I guess is what I'm trying to ask.
Yeah, that's a really good question. I guess our first step will be just building a database and storing everything. And neural network is not a bad idea too. Yeah.
All right, let's continue this offline, please. And Jacques, do you